This is just reference, but you can't see it, is it? Anyway, this I'll just read out. Yeah, okay. Yeah, afterwards I'll write here. This one. Okay, so there's a this series of papers called Random Walks on Lattices. So there's 1, 2, 3, 4, 5, and I don't know if there's more by Montreal and Weiss in this Journal of Mathematical Physics, 1965. So for what I was teaching, I think this is most relevant too. Okay, so some people were a bit confused about this mean number of visits and first passage. So I'll just review what I said. Okay, so so one of the objects we have is this probability. So so there's some lattice in some arbitrary dimension, and you start from the origin, and then you ask what is the you take n number of steps, so that is given number of steps, and you ask what is the probability that after n steps you are at x bar. Okay, so probability of being at x after n steps. This is P of x. And this satisfies that if I sum over all lattice points, then this must be 1. Okay, then I define something called the generating function, which was g of x bar z. Okay, and okay, so this I call the generating function. And then I said that g of x bar at n, so sorry, x bar at z equal to 1. So if you put z equal to 1, then it's just sum of these probabilities at a given site for all times. Right? So this is sum over all times at a given site. And this I gave actually a proof that this is basically the mean number of visits. And then we saw that g of in particular we looked at the objects g of 0, 1. So origin is, let's say we call it 0 vector. So we looked at the mean number of visits. What? Can't hear. Yeah, that's, I thought so. Can someone call Peter? Hello. Now you can hear? No. I think battery is dead. Hello. 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 Now you can hear. Okay. Okay, so this is the mean number of visits starting from the origin, the mean number of visits to the origin. Okay, and this we said in, so this is basically in general it's given by some integral. Right, so there was another factor e to the power I theta dot x, but that x is 0, so that goes to 1. So this is the integral. And then we said in, so g, so let's put the dimension here, gd, let's say. So d is the dimension. So we said g1 is equal to infinity, g2 equals to infinite, and then g3 onwards it's finite. So actually I found the number. So g3 is, and if you look at, so there's a page in where they list actually G1 to G8. Okay, and G8 is like, it's already 0.07. Okay, so so basically as you go higher dimensions, G keeps decreasing. Okay, I couldn't see, find what exactly is the power at large D, but I think it's maybe 1 by D square or something. Okay, so this is the mean number of visits. So then basic point is like, if you are in higher and higher dimensions, the number of times you visit the starting point becomes lesser and lesser, right? Which is kind of understandable. And then we asked the question, what is the probability that, so what did I call it? F, is it? Probability of return. So this, we showed that this is equal to 1 minus 1 over GD. So this is the probability starting from the origin that if I keep walking, I'll ever come back to the origin. Okay, and then we said that these two quantities can be related. And the way we argued is that if you look at the mean number of visits, okay, so I start from the origin, so that's already, I count it as a visit, okay. And then if I keep walking, there's a chance that I may not come back, okay. So the chance of that is 1 minus f, right? So therefore I can write, GD, so there's the mean number of visits consists of visits where there's just one visit, which is like I start and then I never come back. Okay, so that's, so I'm calculating a mean, and the mean is over like one visit, what is the probability? Two visit, what's the probability? Three visits, what's the probability? So the mean number of visits is one visit, the probability is 1 minus f, right? Because I start and then I never come back. What's the probability of 2 visits? Is I start, I come back, and I leave, and then I never come back. Okay, so that is 2 visits, and the probability of coming back is f, and the probability of not coming back is 1 minus f, right? And then similarly, I get a series. 3 visits is plus 3f square. 2, I come back, again I come back, and then I never come back. So 1 minus f. Is this clear? Anyone? It's not clear to anyone? Okay, that's good. Okay, so then this I write, and then you just sum up the series and you get this result, right? Okay, so from this we basically corresponding to all this we get probability in 1D you'll always come back, probability in 2D you'll always come back, and probability in 3D is, so if you do this, it's like 0.34. Any questions? Okay, so can we understand this in a heuristic way? Okay, so so the way you can argue is, okay, supposing you look at a random walk, so it basically looks like this, right? And some random trajectory. Okay, now you can ask, I mean, typically what is the distance it has gone in time t? Huh? Root, no, t to the power half, right? So this distance r. So in time t, half. So if you have gone t to the power half distance, then what is the number of sites you have visited on average? Okay, so therefore number of sites visited is how much? Roughly, I mean, if you have gone this far. Huh? No, in dimension, it will be like, let's say, yeah, it will be the volume of this yeah, right? So it will be r to the power, what, d minus 1. Or d, sorry, d. Okay, so that is t to the power d by 2. That's the number of sites visited. And the total time of the walk is, of course, t. Right? Total time is t. Okay, so therefore, time per site is roughly equal to t divided by t to the power d by 2. Right? So that's t to the power 1 minus d by 2. So you can see that as t becomes large, in one dimension this is like infinity, and greater than 2 it is goes to 0. Right? Huh? So and t equal to 2 is kind of marginal, so it doesn't say anything. But at least you can see that in 1D you visit sites infinite number of times. 2D also it's kind of, yeah, and higher dimensions it goes down. Okay, so I mean, other point I want to mention is that here we looked at the coming back to the origin, like the mean number of visits to the origin, and the probability of coming back to the origin. Similarly, you can ask what is the probability of starting from the origin, and what is the probability that you'll ever visit a site X, right? So, or what is the mean number of visits to the site X? Okay, so so then of course you just put here e to the power I theta dot x, right? But then it's clear that the arguments which give us infinite will still go through, right? Because that came from some divergences in the denominator, right? So this result is still true, that if you start from here, any site will be visited infinite number of times. And the probability of, in 1 and 2 dimension, and the probability of visiting any site is 1 in 1 and 2 dimension. Is that clear? Is it clear? No. Okay, and you should say it's not clear, you should just say no. Okay, so, I mean, is this much clear? This much is clear, this one is not clear, okay. So here what we looked at is probability of a number of, so you start from here and the mean number of visits to this site. And then we asked about what is the probability of returning to this site. Okay, that was what we discussed here. Then you can ask, starting from here, what is the probability you will ever reach some arbitrary site X? Right, I mean, that's also a question. So then I'm saying, then that I should again compute this mean number of visits to this site. Okay, so how would I compute mean number of visits to this site? Exactly, right, yeah. So I would have to look at g of x bar 1, right, the same thing. So then it's the same integral except I have the sum e to the power I theta dot x. So here if I make x bar, I will just get e to the power I theta dot x. So now then you have to ask again, is it still infinite, right? And that is, I mean, it has to be infinite, right? Because this divergence came from small theta. And at small theta anyway, e to the power I theta x won't do anything, right? It will. No, G3, this value will depend on, of course, how far you are, right? I mean, that, yeah, so, okay, so basically, maybe I should say that in 1 and 1 and 2D, it's again infinite. This is clear. And then in higher dimensions, so GD greater than 2, this will of course be some function of x bar, right? And you expect, of course, this should decrease with x, right? Yeah. So I mean, okay. So right now I don't remember. Yeah. So this f of x, okay, let's say mod x. It will probably depend on mod x, like for large x, and it should decay in some way which is related to some solution of some Laplacian kind of thing. So maybe it's 1 by r square or something. I mean, like in 3 dimension. Okay, this one has to compute. Okay, so okay, so this we want d infinity. I mean, see d infinity anyway. This will go to. I mean, it might be like something like that. Time infinite. No, there is no time here, right? Time is already infinite. Like you're walking forever and you're asking what is the okay, so one other thing I wanted to mention is one other interesting property of this random walk is is that if you look at it, it's in dimensions higher than 2. It's actually a fractal object. Okay, so what does that mean? So that means like if you see in a sphere of radius r, like how many points are visited, then it's a very small fraction of this entire volume. Okay. Yeah, that's true. Yeah. No. Okay, so what you are saying is probability of, see, starting from origin to here is the same as probability of starting from, let's say, here and coming back to here. That is same. The number of steps is infinite, right? Yeah. Yeah. No, 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 no. No, see, I mean, yeah. No, I mean, right, yeah. Yeah, yeah, yeah. Because I mean, see, like in 1 and 2, of course, there's no problem. It's anyway infinite. But in, let's say, in higher dimension, I mean, if you ask from here, you're doing work and, okay, what is the probability of coming back here? And what is the probability of coming to some, let's say, some really far point? Okay, then you can imagine, of course, you're walking for infinite time, but many times you'll just go somewhere, right? So, I mean, there's more chance of coming back here than some point really, I mean, your point could be infinite, right? So then, of course, yeah. Yeah, in any distance, see, this is, I mean, you can see that, okay, I mean, from the expression, of course, you can see there's this explicit X dependence. Yeah. But it's not like there's this, it's not translationally invariant in the sense that you are asking from here to some point. So it's not like if you ask from here to here and here to here, it's the same. Yeah. Yeah. Uh, no, see, I mean, this question is not translationally invariant. So, I mean, you can't. Yeah, it's a lattice, but I mean, you are, I mean, it doesn't matter lattice or a continuum. You are starting from here and you're asking what is the probability of, yeah, you're somewhere, I mean, but see, you could have wandered really far. I mean, you could have gone this way. I mean, no, I mean, how can you do that? I mean, no, the equation itself doesn't have, I mean, translational invariance. No, see, you have to, I mean, you have to frame it like, okay, you have to, I mean, the best way is to, if you write down an equation, you can see, I mean, like you have to write precisely what is the equation you're talking about. And if you can write that, then, I mean, but it is definitely not true. I mean, right, yeah. Yeah, right, yeah. Right, yeah. No, it's not, it's not exactly, it doesn't mean it has, I mean, for a particular object, it's anyway, probability is 1. Okay. That is anyway, so it's probability of going anywhere is 1. So in some sense, okay, there is, but it doesn't mean the system is like, for all questions you ask, it won't be true. Yeah. No, I mean, your memory means you're breaking translation to be starting from a point, right? You're fixing a origin. That fixes, I mean, like, why is P of xn? Why does this depend on x, P of xn? This itself, why does it depend on? I mean, because you are starting from an origin. Yeah, I mean, symmetric means here, it's not completely symmetric, but it has some here. Okay, so what I was going to talk about the fractal dimension. Yeah. Okay, so now fractal dimension, basically one way to ask, ask what is the fractal dimension is to, so I mean, if I'm doing this random walk, so then I'll find that after uh, so let's say you start from here and you do some work like that. Okay, so for it, some number of time steps, and then you'll find that so there is some number of sites which have been visited. Okay, and then you ask that in a box of size, in a sphere of size R, how many points are there? How many points have been visited? Okay, so then the number of points, if will typically be given by R to the power. So if all points are visited, then what would n be? Let's say in d dimension. If all the lattice sites are visited, then it would be R to the power d, right? But random walk doesn't visit, it visits a very small number of points. Okay, so therefore it's some fractal dimension df. So and what is this df? Okay, so this df is, repeat, okay. So I'm saying we are trying to find what is the fractal dimension of the walk. Okay, so how do you define fractal dimension? Is like we have a lattice and we start from the origin and we are, so let's say this is a walk of for some time t. So some number of steps and it's somewhere here. Okay, so then in this, so we have, let's construct a sphere and then ask how many sites have been visited. Okay, so the number of visited sites in time t, I call that n. Okay, and so this will, if this sphere is size r, then I ask how many points are, how does it scale with this radius? No, yeah, it can be visited, like typically a random walk will visit each point many times, right? That's what we saw. In 2D, it will visit large number of times. 3D, maybe it's much less. 4D, it's much less. But so most points will be visited maybe just once, in a higher dimension at least. But you allow that also. You just count the number of points that have been visited. It might be multiple visits and so on. Okay, so but you just count the number of points and then you see how it scales with. And so if all points are visited, then this df would just be the dimension of space, right? But typically you'll find that small number of points are visited, and you want to ask what is this? Okay. Okay, so now if the random walk walks for time t, then the radius is typically, we just said it's r square, right? Uh, Right, yeah. So T goes as R square. And so in, let's say, she asked the question, I mean, most sites are typically visited less than one number of times if you are in higher dimensions. Okay. So then T is actually the number of sites visited. Is that clear? See, I'm saying if you ask in time T how many sites are visited, it will be actually T, because most sites are visited just once, if you're in high enough dimension. So let's say higher than 2. So then it's just 1. So therefore T is, n is actually T. Okay. And so, so T goes as R square. And so the fractal dimension of the random walk is basically 2. So df is equal to 2 for d greater than equal to 2. Okay, so now in so higher dimensions, this is clear. In 2 dimensions, actually, what most sites are visited like a large number of times. So then, if you look at the object, it's quite a compact object. Okay, so then of course, if a compact object means most sites are visited, so then it will be the real dimension, which happens to be 2. No, this is I'm looking at a finite time. Yeah, and I'm not always looking at there. I was looking at infinite time, but now I am finite time. Okay, so in 2 dimension, it's a compact object, so it has to be the fractal dimension is the same as the dimension of the space. And in 1 dimension, what is the fractal dimension? 1, right? Because again, it's a compact object, so it has to be 1. So df equals to 1 in compact means like almost every place is visited. I mean, like it's space filling basically. Okay, so I mean, doesn't mean it will look like, I mean, if you look at typical trajectories in random walk, they will still look very kind of, I mean, actually the boundary is again a fractal object with dimension greater than 1. So it's not like a space filling thing, but it's still mostly in a given region, is so like there are very few holes. Okay, so this was kind of recap mostly. And now we want to ask the question, even right, is it? Okay, so I might need this definition. Okay, so now here we ask the question that you start from here and what is the probability you will come back, right? Now next question we want to ask is, what is the probability you will come back for the first time in some time t, at some time step n, let's say. Okay, so we define the object P1, okay, I'll still something like that. Okay, and so, I mean, okay, so this is, I mean, earlier we were discussing this quantity f defined there, which is the probability of coming back ever, right? So the probability of coming back ever, so this quantity is probability of going to any site x for the first time at the nth step, right? So now I can ask if I put here origin, so then, so all this is always starting from the origin, okay? Probability of reaching x for the first time at the nth step, starting from origin. Okay, so so if I ask what is the probability I come back to the origin at the nth time step, so then if I sum over all possible, like what is the probability I come back after 1 step, what is the probability I come back after 2 steps, what is the probability I come back 3 steps, then of course this must be the probability that I ever come back, right? So this quantity is related to the quantity we earlier defined. First time, yeah. This is also, I mean, coming back means it's like, see, what is the probability? So if you do an experiment, what will you do? If you ask what is the probability I come back, so you walk, and then if you come back, then of course you just end the experiment, right? You see what is the probability of this trajectory. Where? No, even here it's probability of coming back means you, when you come back, you just stop. So that's a very important point. I mean, quite often it's you have to think a lot to see what is the difference between this and this, okay. So this is the probability of being at X at time N, okay. That it doesn't mean that you visit, I mean, so if you, I mean, naively it looks like this object and this are like almost the same thing, right? But let's give an example. Okay, so supposing let's just do an example just to make this point clear. Okay, so if I ask what is the probability that after 4 steps I'm here for the first time after 4 steps. Okay, so then okay, and I can first ask the other question, what is the probability that after 4 steps I am at this place? Okay, so there are 2 questions I can ask. After 4 steps, what is the probability of being at origin? Okay, so what is the answer? What is P40? Oh, P40 right here. P, no, not 40. P, after 4 say what's the probability? This is P04. What is the probability that after 4 steps, and this is what we calculated here, right? Probability of being at X bar after n steps. Okay, so this we learned to calculate earlier, right? Using some combinatorial methods. Okay, but how would you do it? So you'd ask what are the possible 4 steps which bring you to the origin. Okay, so let's write all the 4 steps. So the possible 4 steps, okay, maybe it's too much. This is 1 step, 1 path. Okay, so can someone quickly do it? How many paths, huh? How many paths are there which bring me to the origin? Okay, so this is 1 path. Then I can just reverse it. So then I can do 8 such paths, right? So this kind of paths are 8. Are there any other paths? So okay, 4 more means like I can have paths like that. Okay, this is clear, right? Okay. So this kind of paths again 4. But I can have many more. Huh? So I can have like this, like this, like this, like that. So this again, how many? 4 again. And then I can have like that. So that's 1, 2. Okay, any more? Right, yeah. So this again 4, right? Okay, so 8, 4, 12, 4, 16, 17, 18, 4, 22. That's right, is it? Maybe it's, huh? go right. Ah, that's also there, yeah. That's different from this, right? Yeah, so that's, so that again, 8. Which one? Ah, sorry? 4 and what else? This is different now. This will be 8 because you can go like that or you can go like that, and then you can do 4. This will be 8. Okay, so 8 for 12, 13, 14, 14 for 18, 22, 30, 30. Maybe, okay, maybe we might have missed something. Okay, so that's not important. I mean, if you work, you can, but let's assume it's 30. And then what's the probability? 1 by 4 to the power 4, right? Because each path probability is 1 by 4 to the power 4. So 1 by 4, 4 to the 4 and 30. Okay, so we actually wrote an exact formula. I don't know if we can check with that if it agrees, but anyway, that we can do later. Let's assume this is right, okay. Okay, so let's check. Check with okay. Okay, so we had some combinatorial expression. Actually, let me write it because yesterday I wrote it wrong. So let me just write the expression. One second. Okay, so what? Right, yeah, yeah. So this is the correct thing. It's like this is the 1D also you do the same, right? By this is n plus v. Okay, so now we can quickly check if it works. Okay, so here we'll put n equal to 4 and xy is 0. So then you get for to 0, n equal to 4. So that's 1 by 4 to the power 4 and 4 factorial divided by, so this is basically 2 factorial to the power 4, right? So 2 factorial to the power 4. It doesn't work. Oh, there's another n factorial, sorry. Yeah. So this is 36, right? 36. Okay, so we have missed 6 paths now. Okay, 6. 6 is an odd number. How can it be 6? Okay, maybe in the tutorial you can figure out. I know, okay, I don't do it. Okay, but the, huh? This one. It should be what? Okay, this, and then what is the reverse means? Okay, okay, okay. So 8. Okay, then 34. 2 more. This one. Okay, okay. Okay, so plus 4. Plus. Okay. Right, okay. Okay, so that's 36, right? Okay, so it works. Okay, so this is 36 by whatever. Okay, so now, and now let's look at P1, this other object, okay. So how would we calculate this? What is the probability I return to the origin for the first time in 4 steps? Okay, so then what should I do? I should take only those paths which came back to the origin for the first time in 4 steps. Okay, so then it's only this path, right? And maybe this path. This path, it came in the second step, and then didn't, then again it came back. But this I don't care. I mean, it's like this path also I don't care. This one also came back. This one, it's the first time. Sorry? Yeah, this one also. Okay. So then I can calculate it and I'll get some numbers. So that is what. So it's still the probability of all those paths is still 4 to the power 4. And but the number of paths which are contributing is now 8 plus. Okay, so this one is okay. This is okay, and this is okay. So 8 plus 4, 12. 4. Which one? Why it's coming back for the first time? Oh, this one oh, this started from the middle. Sorry, right, yeah. Okay, so it's this doesn't go. Oh, this one is right. Okay, so 4, 8, 12, 20. So that's right. Okay, so this is just to explain that these are 2 different objects and the reason why it's different. Okay. So now, of course, if I want to ask, like, I can then ask what is the probability it came back to the origin for the first time in 2 steps and then 1 step and so on. And then if I want to ask what's the so this is and then 5 steps and 6 steps, then it's clear, right, that if I sum over all n, I should get back the probability of return. So return means it should be first time, right? Because if you ask like the physically, what's the interesting question? Like what's the probability of return? Return means it has to be first time, right? I mean, otherwise return doesn't mean I come back and go and again come back, and that's not return. So okay, so that's so I hope this yeah, statement is clear, right? Okay, so Okay, so now what we'll do is we really want to compute this full distribution. Okay, so right now we know how to, if we sum over all n, then we know this object. Okay, but now we want to actually know exactly what is this object. Okay, so then what we'll do is we'll again, earlier what we did is we saw this one. Okay, in general, okay, so this we can define, okay, so this, yeah, so this, now let's define it for, I can also define it for x, right? I mean, what is the probability I start from the origin and visit x for the first time, second time, and so on. So I can define then this probability of visiting any point x ever. Okay, so this is now, yeah. Okay, so for this summation, what we saw is that to compute this object, it was we related to that G, and then everything was easy. Okay, so now we'll see that similarly one can do the same thing. Somehow you can relate it to G, basically using this idea that of this recursion relation, okay, this kind of recursive, it's gone now. That f equal to 1 minus 1 by g. So the way we built that argument was g was equal to like 1 return, 2 return, and so on, right? So we'll do a similar strategy here. Okay? And for that, we first construct a generating function corresponding to this object. So we'll define f of z x bar is equal to sum of n equal to 0 to z to the power n is p1. This I already explained why. So f1 x bar is basically this object, and I explained why it's the probability of visiting a site. Okay, so now probability of no. So earlier I said if it is 0, then it's probability of returning to the starting point. No. So this is probability of you start from origin and go to x. See, this one, what did I define it? It's probability of starting from origin and visiting x bar for the first time. First time, yeah, it's always first time. Okay, so one thing that it's like I said earlier, it's like a Fourier transform. So if you know this, how do you find this? Inverse Fourier transform. What is the expression? Some contour integral, right? I mean, it's basically So now let's try to relate this f and g. And so let me just write one relation with relating this P1 and P. Okay. So P of okay. So how do I get this? Okay, so now this is very similar to that GF business. Okay, so here basically I'm asking like if I am going from let's say 0 to x. Okay, so now so this is the origin and this is some point x. Okay, I ask what is the probability I am at x at time n. Okay, so this will consist of all kinds of paths, right? So there will be some paths where so I'm looking at time n, let's say. Okay. So there will be some path where I visit this place in like for the first time in let's say some time n, and in the remaining time it's like I start from here and I have to come back here, right? So I have to reach here at some time and then I come back here, but coming back in the remaining n minus n time. Okay, and the remaining n minus n time, I might have come back many times. Yeah. No, so from here to here, I'm saying it's the probability that it goes to the to x for the first time in let's say n minus n steps. Okay, so in n minus n steps, it goes to x for the first time. Okay, and then it just comes back to the same point because it has to be at x. But it's just the probability of being at that place after n time. So it might be many like returns. It's not one return. This one is the first passage, but this one need not be first passage. So that's what I'm saying. It I mean it goes. This is first passage. After that, it could be many passages, but after n time you are here. So this is 0 bar means you start, okay, so this is maybe a bit confusing. So what I meant is you go to x, right? And you come back to x. So x to x is like 0 to 0, right? That's of course true. I mean like any point is the same. So x, so this I should really write starting from x and return to x in time n. But that is same as 0 to 0 because it's everywhere is transitioning. Okay, so this actually you should really make sure you understand this. Any other questions on this? That is okay. That you can do. Yeah, I mean, yeah, that's what I was starting with, but it's the same thing because you are summing from n equal to 0 to n, so it doesn't matter. Okay, so this is clear, right? And if your x is the origin, then I need to include one point, which is because I said that if I start from here, then of course it's already 1. So if n is 0, it's already 1. Okay, so these are the two relations that I can write relating this P and P1. Okay, so now we will, given this kind of relations, this kind of recursion relations, the easiest way to, so we know this object FP, we don't know P1, right? And the way to do this is using this generating function method, it kind of becomes easy. So it's again, it's basically like Fourier transform. In some variables it's difficult, but if you transform it becomes easy because they decouple. Okay, so here everything looks coupled, right? Once you go to this generating function, then they become decoupled. Oh, sorry, n minus n. Okay, so now we do the same business like multiply by z to the power n. Okay, let me just write it. So multiply by z to the power n and sum over n equal to 0 to infinity. Okay, now when you have something like this, so let's say you have n equal to 0 to infinity summation n equal to 0 to n. So this I can, when I do the summation, I can write it like this, and then I can, so I can rewrite it as two summations, right? So this is like some dummy index, and then if I change variables, one can see that both go from 0 to infinity. So this basically gives me, so this is the generating function. This one summation gives me the generating function for the first year, so that is z x bar, and the other is g of 0 bar z. Right, this is okay. So therefore, from the first equation, we get g x bar z is equal to f of and from the second equation, we get g of 0 bar z is equal to 1 plus. Okay, so from okay, so now basically we have got the generating function f in terms of g. Okay, so if you put z equal to 1, we get back the earlier result, and but now we have more information because we have some z here, which corresponds to information about time, right? Because if we take inverse transformation, we'll get basically p1 0n, and similarly we can do it at any site. Okay, so this all, so all this is known. So now we have this. So now, okay, how much? Yeah. What equal to 1? Z equal to 1. Z equal to 1 is the previous. Okay, yeah, maybe there are too many indices now, so it's a bit confusing, but okay, so now like we started by saying what we're interested in is trying to say something about what is the probability of return in some time t, right? So we'll basically, okay, so we could have also asked what is the probability of going to some point x in time t, which we would have to analyze this, but we'll just stick to looking at like returning to the origin in some time t. So we analyze this equation now, right? So from this we have to somehow figure out how to get the like p1. So G, and okay, so this one, if we sum over n, will we? So this is a probability distribution in n, right? But so if we sum over n, will it always give? It doesn't always give 1. That you should remember, right? Because in 1 and 2 dimension it will give 1, but in higher dimensions it's something which is actually less than 1. Okay. So there's some probability of not returning. So that's an important point. Okay, so how do you get this from? So now the basic idea is that in general, so supposing you look at this generating function, Cz is equal to summation P of n. So I'm just dropping other indices and just writing z to the power n. Okay, so if you know this, how do you say something about this function? Okay, and what we'll try to say is at least say something for large n. Okay, so usually one is interested in asymptotic properties. Okay. Huh? Yes? Oh, sorry. That was Z, right? Yeah, there's Z. Okay, so typically we'll be interested in P. Okay, so now. Okay, so large n actually corresponds to looking at the behavior of this function. If you want to find how does Pn look at large n, it corresponds to looking at g at small z, z close to 1. Okay, so let me explain why. So supposing you write okay, so then the summation is G of S. I can let's call some new function G tilde S is equal to sum over Pn this, right? So I mean, if you're looking at large n, then I mean this function decays very fast, right? So I mean, if unless you take s small, I mean this will decay very fast. So if you are if n is large means you have to like small s many terms. Okay, no, sorry. What am I saying? So if s very small, so let's say s is like close to 0. Okay, so then if s is very small, then it's clear that in this summation you have to take a large number of terms, right? If s is large, then since it's decaying exponentially, so it will decay very fast, right? So in this summation, only a few point terms will dominate. Let's say P1, P2, let's say it's 1000, then P1 will describe everything. But if S is small, then you really need to take a large number of terms in this summation. Okay. So for S really small, what you can do is it's clear that you have to take large number of n, and then you can write this as an integral. Okay, so like many examples, where you have a summation and you can convert it in integral, and typically you can do that if it's a slowly varying function. So so in that case, you can write it as g tilde s is equal to integral p of n e to the power minus n. Okay, so n is 1, 2, 3, 4, but if it's n is large, you don't care, you can call d of n is equal to 1. Okay, so dn is 1 and you just write like that. So this is the same. Okay, so now let's say for no, so I'm saying if you are okay, so if you look at this integral, okay, this object out here, I mean if s was large, of course it would look like that. Okay, so this is n equal to, so as a function of n, you are plotting the integrand, supposing. Okay, if s is large, it would look like, but if s is small, then it looks like something like that. Okay, so then you can really go to the what is called the continuum limit. Okay, so then like dn is 1 is okay. I mean you can just convert it directly into an integral. Okay, and so you can write like this. Okay, this is what you do when you, let's say, calculate things like density of states, like in solid state physics, and this is exactly what you do. For large n, I mean you just convert like this. Okay, so now you have something like this, and then let's say, okay, so this is, so now it's clear that when you do this integral, this will be the same as 0 to 1 by this. Okay, so I mean this function decays exponentially, so and over a length scale 1 over, so n is the variable, right? So after about 1 by s, it's very small. So I can restrict the integral to 1 by s and then forget about this. So it's basically given by this. Okay, so now, so typically what you find is that in many examples, this P of n might be a power law. Okay, so assume it's, and what we want to find is the power, the exponent. Okay, so assume that P of n okay, so then this becomes So this is minus 1 minus mu. Okay, so right now it looks like this might diverge at small n, but here actually this, I mean, we are most interested in large n. Okay, so here when I say power law, it doesn't mean it's power law even at n equal to 0, right? It's usually it will be a smooth function. So here, I mean, I don't care, I can put some cutoff. So the divergence is whatever is coming is from the large, small s. So s is small, so this is large, and that's where it's coming from. So then you get s to the power mu minus 1. Okay, maybe I write it as 1 by s to the power 1 minus mu. Okay, so what we saw is that if Pn has this form, power law, then this generating function at small s will behave like 1 by s to the power 1 minus mu. Okay, so this is s going to 0. Any questions? So see, this first I said that I mean I have an exponential function like that, and this will of course decay over a scale 1 by s, right? So after that I can just forget it. I can, and out here I just put it as 1. So I mean, so this is a heuristic argument, but then it can, you can make it rigorous. Okay, so people have made it, I mean, completely rigorous. I'm just giving a kind of physicist way of doing things, which will give you the correct result. Okay, so this I hope. Any other questions? I mean, I can repeat it because maybe it's a bit dense. Questions? Actually, I can work there. Okay, so now let's do one example of how do you find in 1D. Uh, can I say something about P1, 0, in what is the distribution of return times to the origin at large n? Okay, so what should I do now? What's the first thing I should do? Calculate the generating function, right? And so do I know the generating function? F Z0 is 1 minus 1 by G Z0. And what is G0Z in 1D? No, G01 was infinite, right? G0Z is, there's an expression, right? So that expression was 1 by 2 pi minus pi 2 pi d theta 1 by this was the, okay, so yeah, this is right, right? Okay, and if z equal to 1, this blows up, right? But for z less than 1, it doesn't blow up. And we want to compute this. And specifically for z very small, right? Z like close to 1. So we can put z, let's say, equal to e to the minus s. And if s is small, this is like 1 minus s. Right, so this is basically 1 by 2 pi 1 minus, so z I can just replace by 1 minus s. So that's 1 minus s cos theta. Okay, or okay, so this okay, maybe okay, so here again this the main contribution comes from small theta. Okay, so you can kind of replace it by let's say 1 minus, yeah, so this is, you expand this, so it's 1 minus theta square. So this is 1 minus z and this integral one can do, and I'll just write the answer. So this is goes as 1 by 1 minus z to the power half. And in terms of s, since z is for small s, z is like 1 minus s. So if you replace this, this is like 1 by s to the power half. Okay, so okay, so now we basically go back to that this result. Okay, so I mean, we know that if whatever S0 is equal to or this is how we defined. And now we know that if this behaves as, if P behaves as 1 by n to the power mu, then this should behave as 1 by s to the power 1 minus mu. Okay, so right now we found how this f behaves is s to the power half. So therefore half is 1 minus mu. So therefore 1 minus mu is equal to half and mu is equal to half. Okay, so therefore, I mean, so now we know what is P1. It's just 1, so P1 is, that's not right. Okay, so there's a mistake here somewhere. Should it be 1 by 3 by 2? 1 minus mu. Okay, yeah, so what was the mistake? Maybe, I mean, is this, yeah, so this actually is for G, right? And I want F, I mean, I still didn't, so this is G and this is this, so what we have proved is that P goes as, so I should write G here. So if I wrote G here, then this tells me that P n0 at large n goes as 1 by n to the power half, which is true, right? Because for, we know from this is just the usual probability of being at the origin after large time n, which is like e to the power minus x square by root t, and t is just this. So this is correct. So we still haven't found P1. So for P1 now this is G, and now we have to calculate F. Right? So F is, okay, I'll just call it S, is equal to 1 minus 1 by G. So then it's 1 minus S to the power half. Okay, and maybe there's some coefficient here, so I'll call it 1 minus S to the half. Okay, so now this is not exactly in this in this form. So, but I go back to the original relation I wrote. So we wrote that f of s or tilde, so let's call it tilde. So when I use s, I will call tilde. If I use z, I call f. Okay, so if tilde s was given by and this we see is has the form 1 minus a is to the power half. Okay. Now, what can P1 be? So, what you can do is you can take a derivative and okay, so here s equal to 0 means this is like return probability, so that's 1. So in more than, so in 1 and 2 dimensions you'll have this 1. In higher dimensions you won't have this 1. Okay, so there it will be pure power law. In 1 and 2 dimensions you'll have this additional factor of 1, and then you have to write it like this. Okay, and from this you can see that this is true. Okay, so let me just explain from here to here. Okay, so what you can do is, supposing you put, supposing you put 1 by s is equal to n star, and so then you have some f tilde, so some new function a n star is equal to 0 to n star. So now if I take a derivative with respect to n star, so dA by dn star is equal to p1 n star, right? So what I should do is, given this function of s, I should first write it as some new variable with as n star, and then take a derivative. So that will give me p1 n star, and then I just replace n star by s again. Okay. So okay, so this is like, given this integral, I can invert it by just doing this. Okay. So since I know the left hand side, I can take a derivative, and then I should put s equal to 1 by n. Okay, so that will give this p1n equals to 1 by n. Okay, so I mean, this thing that I mentioned will work in like higher dimensions. In 1 and 2 dimensions, you have to really use this step. Okay, but the basic point is that once you see the smallest behavior, you can somehow figure out what this should be. Okay, so now our main result is that, so this you see is very different from this, right? So the probability you'll come back to the origin at the nth step decays as 1 by n to the power 3 by 2. Okay. While the probability of being at the origin at the nth step is 1 by root n. So they are completely different objects. Okay. Any questions? Okay, so let me try to finish. Okay, so you can also do this in 2 dimensions. So if you do in 2 dimensions, so first you have to compute the g function, and then the so then g is of course 1 by 2 pi square d. So if z is there, so cos theta 1 is, so this is g of, and then again you have to compute it for z very close to 1. So let's say z is 1 minus this. Okay, so if you do this in 2 dimension, what you get is g. Okay, so there that thing g of s become infinite at small s as 1 over root s, and in 2 dimension it again becomes infinite as minus log s. Okay, so of course at s equal to 0 it has to be infinite, right? We already proved that. And how does it become infinite? As logarithmically, and there it was like 1 by root s. And so f tilde is 1 minus this, so and there's some constant, okay, where you have to write some constants, so log s. Sorry, 1 by log s. Okay, and then we say that this is equal to 0 to 1 by s dn p1. Okay, and then again you can do that same trick, like take a derivative, put 1 by s equal to n star, and then take a derivative, and then again put n star equal to 1 by s. Okay, so if you do that, you get P1, and now it is P1 is equal to right, okay. So, okay, so this is the probability of return to the origin in time n in 2 dimension. So what is this in 2D? For large n, what is this? Huh? No. This is the probability that you are at the origin at some large time n. No, this is the other object, right? There were two objects, P1 and P. So now I'm asking P in 2 dimension, if I put x bar equal to 0, at large n, what does it look like? Someone should say this. I mean, this is the simplest thing I taught. Huh? No, it's not 1. I'm asking P of, okay, this is really the simplest thing I taught. At large n, what does it look like? This one knows in any dimension. N to the power? N to the power? Half. Minus half. Okay, no, almost. I mean, in 1D it's n to the minus half. That's what we wrote. Minus d by 2, right? Yeah. Why? Because, I mean, you can just say it from the Gaussian, right? I mean, this one, it's roughly at large times, it looks like in any dimension, right? X squared by n by I mean, time to the power d by 2. This is true for any dimension, right? So if you put x equal to 0, it's just 1 by n to the power d by 2. Okay, so so this is 1 by n. Okay, and this one is slightly different. It's there's a log n square correction. And in 1D we saw this is 1 by root n, and this is 1 by n to the power 3 by 2. Okay. So and in can you guess what is it in this in 3D? So okay, 3D, let's say. Okay, so 1D. I mean, 3D, what? Huh? Okay, this is what? N to the power 3 by 2. And this one? Huh? Square root. No, okay, so I mean, see, roughly it's not, here it was drastically different. Here it's almost same. I mean 1 by n, then there's log n square. Log n square is not so big correction, right? So you might expect that it should get closer to this. So maybe n to the power 3 by 2 and something, right? So it turns out it's actually exactly 3 by 2. Okay, so in any dimension higher than 2, it's so this is t. Okay, so this again, it's easy to like if you just have to find this g in any dimensions at small, like if you're looking at small s, you can do this integral and you can show that it's easy to prove that this is true. And this is related again to the fact that in 3 dimensions there's not many crossings, like you don't come back, and so therefore these two results are almost the same, right? Because if you remember the way we constructed this example of this 2D case, we had to rule out paths which were, when we constructed P1, we had to rule out paths which came back many times, right? But in higher dimensions, in fact, most paths don't come back many times, right? Because that's, the coming back probability is small. So therefore, they are almost the same in higher dimensions. Okay, so okay, maybe last one thing I'll just mention is I mean, one related question that one asks in this first passage problem is what is the survival probability of the walker? Okay, so this is the probability it comes back to the origin. You can ask the converse question, what is the probability it survives? Means it doesn't come back. Like it's like there's some, if it comes back to the origin, it gets killed, right? So how long does it survive? So what is the probability it survives for time n? Okay, so so I can call it, let's say, S of n. The probability that it survives till time n. And actually it's, so if you look at, so I'll just write the results in 1D. So in, okay, let's ask the question S infinite. Okay, so what is the probability it survives if forever? So, sorry? 0, right? Okay, so, or let me write. Okay, so in 1D, the result is, okay, so let me just write it first. 1 by okay. So see, this is the result in this 1D, and basically this and this are related. Okay, so P1 is actually minus ds by dn. Okay, if you think of in the continuum limit. Okay, so that's because, or in the discrete case, you can write P of n, probability that it returns at the nth step is equal to probability, is the probability that it survived till time n minus probability it survived n plus 1. Okay, so this you have to think a bit, but this is true. And this in the, like if you take large n, then you can convert it into a derivative, so this is true. Okay. And so then you can see that if you take a derivative, you get 1 by n to the power 3 by 2. If you take a derivative, it's 1 by that, and this one is, this one gives this. Okay. Okay, now if you, question is, yeah, n infinity, yeah, infinity, this is 0, this is 0, and this is what? Okay, so what is this in 3D? 3D, the probability, the particle, of course, survives with, I mean, there's a probability, so in 1 and 2D, the probability goes to 0, and in 3D, there's a probability that, so this is, this should go to a finite number. Okay, so this is the, yeah, so why is it not that, right? So this is this gives the probability of like given that a particle gets killed, what's the probability for such particles? It's the survival probability till time n. Okay, there are some particles which get absorbed, right, killed, right? So some fraction of particles get yeah. So you can ask, so what is this object? I mean, this is the probability of those particles which get absorbed. For them, it's the return time distribution. Right? There are a large number of particles which never return. So for them, this result doesn't make sense, right? It's only for those particles which return. Given that a particle returns to the origin, what is the probability it took time n? So that is this object. And for those, you can ask what is the survival probability of those particles. Okay, so maybe I guess we are out of time. So more or less I've covered, I mean, I couldn't talk about linear response. And so what is there anything? Okay, so maybe I have these 2 lecture notes which I'll scan and put it on the webs in my in the school website. And right, yeah. So if you have other questions, you can ask me later. I mean, during the school. Yeah. Sorry. Ah, yeah. You are getting the same thing, but that's okay. No, so that's what I just said. So this is only valid for, so see, there are large number of paths which never return in 3D, right? If you, so there's only a fraction of particles which will return to the origin. So given that it returns, you can ask what is the distribution of the return time. No, so see those for those probability which are returning, for them of course the survival probability goes to 0, right? This is only you are looking at the particles which return. So the survival probability of course is some finite number. But this is just for those which return the, so okay, so maybe I should add, I mean this is just for the particles which do return. It's not 0, right? Yeah. Yeah. No, so this this is survival probability of those particles which do return. So they of course don't survive, right? Because there are some particles which do return. This is like a conditional survival. You can think of this as a conditional. In 3D. Yeah, it says like 0.3 fraction of particles return. Huh? Survival probability is not 0, right? Yeah. So this is only the result for which return, for them, how does the survival probability decay? That is, of course, 1. Of those who don't return is 1, right? They survive forever, I mean. Yeah. If they return, no, what is 0 survival probability? No, but you are asking what is the probability they survive till time n? It goes to 0, but you are asking how. Say again. Ratio of number of particles? That of course we know the number, right? No, I still don't get your question. So you're asking, no, what do you want to calculate? Yeah. Survival probability in 3D, it's of the, see, in 3D we said some particles like definitely survive forever, they don't return. Right, so, I mean, they don't even return. So, I can't calculate the probability that they survive till time n. So, when there then there are some 0.3% of particles, 0.3 fraction of particles, which do return to the origin. For those guys, I can ask what is the probability that they return at time n, or they survive till time n. Right? So that's for those set of particles. Yeah. Right. Yeah. 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 So for those particles, I can ask first. Sorry. Yeah. I'm not considering those 0.7 thing. Right. Yeah. Right. Yeah. Yeah. Right. Yeah. Okay, so it's good people are thinking, I mean, because probability is really, I mean, you have to, like, everyone gets confused. I mean, this difference between P and P1, I mean, like, a lot of people, it's very hard to convince them that they're different, okay. Like, I have had many bets with people, they said it can't be different. Okay, and then, of course, you work out an example and you see it's different. So, I mean, but the good thing about probabilities is like you can understand everything rigorously. Okay? I mean, that's like statistical physics is a kind of rigor. I mean, it's the most rigorous of like branch in physics. Uh, okay, actually, one other thing I want to say is there's a very nice book by. So this is the Polya problem. So he's written a very nice book called uh, How to Solve It. So it's not on random walks, okay, but it's a very nice book. You should